Welcome to Quiet Universe, where we explore the vast unknown and unravel the mysteries of the cosmos. Imagine a structure so immense it could encircle an entire star, capturing all of its energy, enough to power civilizations beyond our wildest dreams. This is the concept of the Dyson Sphere, a theoretical megastructure that pushes the limits of human imagination and technology. We'll dive into what it could mean for the future of humanity, the search for advanced civilizations, and the untapped potential of harnessing the power of stars. Imagine standing in the quiet of space, looking at a star, a distant sun burning brightly in the cold vacuum. It's an untouchable force, massive, violent, yet serene from afar. Now, try to envision harnessing every bit of its power, all the energy it radiates, and using it to fuel the needs of an entire civilization. The idea itself feels like a thought experiment pulled from the fringes of human imagination. But this isn't just fantasy. It's the foundation of what we call a Dyson sphere. A Dyson sphere, at its heart, is a theoretical structure that completely encompasses a star. It captures its energy output, not just a fraction of it, but every ray, every photon, turning it into usable energy. This isn't a simple solar panel on steroids. It's more like engineering on an insane scale. And yes, we're talking about something that would need to be built around a star. When we think about this concept, it forces us to confront the sheer limits of human ambition and ingenuity. You don't just put up scaffolding in space and start hammering away. This is beyond any scale of construction we've ever considered. Imagine the resources, the effort, the technical knowledge that would be needed. It's staggering. But why even think about something so far out of reach? Well, humans have always pushed against boundaries, whether it's scaling mountains, reaching the moon, or exploring the depths of the ocean. And as we grow as a species, our energy demands will grow too. The Earth can only offer so much, and even the sun, from a distance, gives us just a fraction of its power. So, naturally, the idea of harnessing a star, one of the most abundant sources of energy in the universe, is a tempting thought. It's one of those things that feels like the ultimate challenge. Can we, one day, control the very force that has fueled life for billions of years? But there's a haunting silence that comes with the concept of a Dyson sphere. It makes you wonder, if we've thought about it, has someone else already done it? Some scientists have speculated that if such structures existed in the universe, they might be detectable. Imagine a star completely shrouded in a megastructure, its light obscured, only faint traces of infrared radiation slipping through. To us, from millions or billions of light years away, it might look like a star that's dimmed unnaturally, a cosmic signature of something extraordinary at play. The thought stirs up the old question of whether we are truly alone. Could there be other civilizations out there, far more advanced, who have already achieved what we only dream of? And what would it mean for us to discover something like that? There's a strange balance between awe and unease when thinking about a Dyson sphere. On one hand, it represents the pinnacle of human achievement, the idea that we could, in some distant future, manipulate entire stars for our needs. But on the other hand, it forces us to reckon with the idea of limits. What happens after that? What comes after you've mastered the energy of a star? Do you move on to something larger? Or does the endless chase for energy and control ultimately lead to a kind of quiet emptiness, where everything you've pursued feels small compared to the vast, indifferent universe that surrounds you? It's easy to lose yourself in the technical details, the megastructures, the energy output, the engineering marvels. But at the heart of it, the concept of a Dyson sphere is a reflection of human ambition. It's about our drive to control our environment, to find new ways to survive and thrive, no matter the odds. We're always dreaming, always reaching, even when the object of that reach is a star millions of miles away. The question isn't just whether it's possible, but whether we'd ever stop trying to make it so. That's the thing about Dyson spheres. They're as much about philosophy as they are about science. They force us to ask questions we may never have considered. What is the future of humanity if we can one day harness the energy of stars? How does that change who we are, how we live, what we value? And perhaps most importantly, is this truly what we want? To dominate the cosmos in the pursuit of energy? Or will we discover that, like all grand ambitions, it leaves us chasing something we can never fully grasp? There's a certain beauty in that uncertainty. Encompassing an entire star feels like something out of an impossibly far-off dream. Think about the sun, the heart of our solar system, an immense ball of fire and energy that's over 1 million times larger than Earth. Now, Imagine trying to build something that wraps completely around it. The sheer scope of that is mind-blowing, a task that pushes the limits of our understanding of what's possible. Every single day, the sun pours out more energy than humanity could ever use in 1,000 years, but most of it just disappears into the vastness of space, untapped and unreachable. The idea of a structure surrounding it isn't just about ambition, it's about control. It would mean creating something that could harvest every bit of energy, ensuring nothing is wasted, and that the full potential of a star's power is at our disposal. If you think about the size of that project, it becomes hard to wrap your mind around it. This isn't just throwing a few satellites up there or building some massive space station. You're talking about constructing something that stretches across a distance of nearly 1.4 million kilometers, a massive shell or swarm of structures, all functioning in unison to catch the sunlight and convert it into usable energy. The logistics of that alone are staggering. Where would the materials come from? How would you even begin to coordinate such an enormous operation in the empty, hostile environment of space? It's a task that, right now, feels beyond our reach. And yet, there's a beauty in the scale of it. It's the kind of challenge that gets people thinking about the future of humanity, how far we can go, how much we can accomplish. Humans have always pushed the boundaries of what we thought was possible, from the first time we looked up at the stars and wondered what they were, to landing on the moon. Encompassing an entire star feels like the next evolution of that curiosity. It's not just a question of whether we could do it, but what it would mean if we did. If humanity ever managed to build something that surrounds a star, it would be the ultimate sign that we had truly mastered our environment. We would no longer be at the mercy of limited resources on Earth. We'd have an endless supply of energy, more than enough to power whatever future we could imagine. But the concept is also humbling. There's something almost frightening about trying to wrap your mind around the idea of containing a star. Stars are primal forces of nature, massive objects that have existed for billions of years, giving life and light to entire systems of planets. To encompass one, to build a structure that not only interacts with but encircles it, feels almost arrogant in its scope. It's like trying to bottle up the ocean, controlling something that's far beyond our everyday experience. And yet, it's that very impossibility that makes the idea so compelling. To try to encompass an entire star would be a testament to the human spirit, to our relentless drive to explore, understand, and reshape the universe around us. But there's a darker side to it as well. The idea of surrounding a star, of taking all its energy, raises uncomfortable questions about our relationship with nature and the cosmos. What kind of civilization would we need to become to undertake such a project? Would it be a society focused solely on the accumulation of power, on dominating and controlling the very forces of nature? Or would we be something more? A species that had learned to live in harmony with the universe, using its resources responsibly and sustainably. Encompassing an entire star is not just a technological challenge, it's a philosophical one. It forces us to think about what kind of future we're heading toward, and what we're willing to do to get there. In the end, the idea of encompassing a star is more than just a massive engineering project. It's a symbol of human ambition, of our desire to reach for the impossible, and of the potential and risks that come with trying to control forces far larger than ourselves. The thought of harnessing 100% of a star's energy output taps into something both exhilarating and intimidating. It's not just about getting a better source of power. It's about capturing the total force of nature that a star embodies. Stars are these mind-boggling engines of nuclear fusion, constantly burning and releasing energy in every direction. That energy fuels life on planets, drives climates, and can spark entire ecosystems, but most of it is lost to the vast emptiness of space, radiating outwards into infinity, never to be used or captured. The idea of taking every single bit of that energy, turning it into something usable, feels like gaining access to the ultimate resource, more power than humanity could ever dream of needing. To put it into perspective, the sun alone generates around 3.8 times 10 to the power of 26 watts of energy every second. That number is incomprehensible, and yet, this is what a Dyson sphere or any such structure would aim to capture. When we talk about harnessing 100% of a star's energy, we're talking about a level of abundance that would transform civilization as we know it. Energy scarcity, a constant in human history, would simply vanish. No more worrying about fuel sources, no more balancing energy needs against environmental damage, no more searching for alternatives. It's like suddenly having infinite wealth, but in the form of energy. the very thing that powers everything we do. But there's a surreal aspect to this idea as well. It's like playing God with one of the universe's most powerful forces. How do you even begin to fathom controlling every photon that a star emits? There's a strange sense of overreach in it, like we'd be meddling with something so fundamental that it almost feels unnatural. But at the same time, this is what humanity has always done. Found ways to use the resources around us, pushing further with every discovery. We went from burning wood, to coal, to splitting atoms, and eventually, we look to the stars not just for wonder but for power. Harnessing the total energy of a star doesn't just represent an engineering feat. It marks a turning point in human history. We wouldn't just be a species on a planet anymore. We'd be a species that controls stellar power. That kind of achievement would redefine our place in the universe. No longer bound by the limitations of our planet or its resources, we could venture further, explore more, and maybe even find a way to survive for eons. It's the ultimate escape from the limitations that currently hold us back, a way to unlock a future we can barely imagine right now. But there's also a tension here. Just because we can harness a star's energy, should we? It's a question that goes beyond science and technology, venturing into ethics and philosophy. What would humanity become if we had access to limitless energy? Would it free us to pursue a higher level of existence? Or would it lead to overconsumption, stagnation, or even conflict? Imagine what it would be like if every civilization reached out for the energy of their star. Would that make space the new frontier of competition as nations and corporations fight over who controls the most stars? Or would it force us to rethink our values, teaching us to use this immense power with caution and wisdom? Then there's the sheer mind-bending logistics of it. You can't just build a solar panel big enough and call it a day. To harness all the energy a star gives off, we'd need structures so vast that they stretch our imagination. Whether it's a Dyson swarm of countless satellites or a solid sphere surrounding the star, the infrastructure needed to capture 100% of that energy output is something we can barely conceptualize. We're not talking about decades of work, but centuries, even millennia. It's a project that would span generations, with every step forward pushing the boundaries of what we know and what we think is possible. Yet, the appeal of harnessing 100% of a star's energy is undeniable. It's the ultimate solution to the energy problems that plague us today, the thing that could open up entirely new possibilities for humanity. And while it seems far off, almost like science fiction, the very fact that we can think about it, that we can imagine it, says something profound about us. We are, after all, a species that constantly reaches beyond its grasp, always striving to turn the impossible into reality. The star's energy is there, whether we can take it or not, and one day, if we dare, we might just find a way to make it ours. When we think about the materials required to build something that could encompass a star, it's not just a matter of collecting more of what we already have. This isn't like scaling up a skyscraper or building a bigger bridge. It's stepping into an entirely new realm of construction that pushes the limits of what we can even imagine. The sheer amount of resources needed would be astronomical, far beyond anything humanity has ever gathered or used before. It's almost as if we'd have to mine entire planets or strip moons of their materials just to get started. And even then, we might not have enough. The magnitude of such a project forces us to rethink what's possible and what we're capable of. Consider that the Earth itself doesn't have the raw materials to construct something on this scale. We'd need to look beyond, into the rest of the solar system, tapping into the resources of asteroids, other planets, and moons. Mining operations on Earth are already complex and environmentally challenging, so the thought of scaling that up to an entire solar system-wide effort feels almost absurd. Yet, that's what it would take. We're talking about the kind of materials that would have to be incredibly strong, lightweight, and durable, able to withstand the extreme conditions of space and the constant bombardment of solar radiation. You can't just throw steel and concrete at this. It would demand materials that might not even exist yet, at least not in the forms we need. It's not just about the quantity either. The logistics of gathering and transporting these materials would be mind-blowing. Right now, getting a few tons of cargo into space is a massive undertaking. Sending up enough material to build a structure, or swarm of structures, around a star? That's orders of magnitude more difficult. We'd need technologies that could efficiently extract, process, and transport these resources across unimaginable distances. There's also the human element in all of this. How many people would be involved in such an effort, and for how long? It's a project that would likely take centuries, even with the best technology at our disposal. Generations would come and go, working on something they'd never see completed, all in the hope of building something that could one day change the fate of humanity. The scale of the materials required also raises questions about our relationship with the universe. We're used to seeing Earth as our home, but to gather what's needed for something like this, we'd have to expand our view. Suddenly, the solar system becomes our quarry, a source of raw materials to be harvested and repurposed. There's something both thrilling and unsettling about that idea. On one hand, it suggests a future where we are no longer bound by the limitations of our planet, where we can tap into the vast resources of space to fuel our ambitions. On the other hand, it forces us to confront the possibility that we might exploit other celestial bodies in the same way we've exploited Earth, raising ethical and environmental questions on a cosmic scale. But perhaps the most challenging aspect of this is the unknown. There are materials we rely on today that didn't exist a century ago, like the silicon chips in our computers or the advanced composites used in spacecraft. What kinds of materials will we need for a project of this magnitude? Some scientists speculate that we might need to invent entirely new forms of matter, substances that can function in ways we can't even conceive of yet. It's not just about what we can mine or fabricate today. It's about pushing the boundaries of material science itself, developing technologies that can harness the fundamental building blocks of the universe in ways that go far beyond our current understanding. The daunting nature of this task doesn't just lie in the technical challenges or the staggering amounts of material. It's in the sheer scope of the vision. It requires us to think bigger than we've ever thought before, to imagine a future where humanity isn't just a species that lives on Earth, but one that shapes entire solar systems. And while it may feel like an impossible dream, the fact that we're even considering it is a testament to the kind of audacity that defines human progress. It's the kind of challenge that forces us to rethink what's possible, to imagine new ways of interacting with the universe, and to embrace the idea that even the most outrageous visions might one day become reality. The idea that something as vast as a Dyson sphere or a similar megastructure could be detectable by its unique infrared signature introduces a whole new way of thinking about our place in the universe. Imagine looking out into the cosmos, hoping to find evidence of advanced civilizations. It's not like they leave a welcome sign or beam radio waves directly to us. But if a civilization was harnessing the full energy of a star, they wouldn't be able to hide the sheer amount of heat that process would generate. Even though they'd capture all the visible light from the star, turning it into usable energy, the leftover heat has to go somewhere. And that's where the infrared signature comes in. Energy that can't be used still radiates out. And in this case, it would appear as a very distinct glow in the infrared spectrum. This glow wouldn't be something subtle, either. It would be a loud, obvious sign that something massive and artificial was happening around that star. The thought of it is strangely eerie. We could be looking at the remnants of another civilization's work, something so advanced that it's harvesting energy on a scale we can barely imagine. The stars themselves, usually cold and distant in their predictability, could suddenly take on a new dimension, revealing secrets through a type of heat signature that doesn't match the natural order. And that's exciting because it means that we might have a way to detect alien civilizations without them ever needing to reach out to us directly. For scientists, this possibility opens up endless opportunities. Instead of waiting for a signal or trying to pick up radio waves from space, we can scan the sky for these unnatural heat signatures, looking for stars that don't quite behave the way they should. The universe is filled with natural infrared sources, galaxies, stars, planets, but something harnessing 100% of a star's energy would stand out like a beacon. It wouldn't look like anything we've seen before. And the thought that we could be staring at one of these signatures right now, not realizing it, is almost haunting. The key to discovering other intelligent life could be hidden in plain sight, if only we knew exactly what to look for. But there's also a humbling aspect to this. If we detect such a signature, it means that another civilization has already achieved something we're only just beginning to dream about. They'd be so far ahead of us in terms of technology and understanding that it's almost hard to comprehend. While we're still struggling with our energy sources on Earth, they've figured out how to capture the energy of an entire star, reshaping their entire solar system to suit their needs. In a way, it makes you feel small, but also hopeful, because it shows that it's possible. Somewhere out there, in the cold, dark stretches of space, another civilization might have found a way to survive and thrive by harnessing a power source we're only just beginning to imagine. At the same time, the idea of being detectable by our infrared signature makes us rethink our own future. If we ever did manage to build something like this, we'd be putting up a massive signal to the rest of the universe. We'd be announcing our presence to anyone else who might be out there, watching. That carries a certain vulnerability. What would it mean to be visible on such a grand scale to other civilizations who might have different intentions? The thought of being seen by the universe, not through our actions or broadcasts, but through the heat we radiate, adds an extra layer of complexity to the whole idea. The search for these infrared signatures is more than just a hunt for aliens. It's a glimpse into our future. It's a way to peer into the possibilities of what humanity could one day achieve. And in the process, it forces us to consider the universe in ways we never have before. Not just as a backdrop for our existence, but as a canvas filled with other players, all potentially working with forces far greater than we can currently comprehend. When you think about a Type 2 civilization on the Kardashev Scale, you're talking about a level of advancement that's difficult to wrap your head around. This is a civilization that doesn't just scrape by with the energy it can find on its planet. Instead, it taps into the full energy of its star, literally harvesting the power of an entire sun. For us, living in what would be considered a Type 1 civilization, where we're still figuring out how to make renewable energy work on a global scale, the idea of controlling all the energy output of a star feels almost mythical. It's a level of mastery over nature that turns science fiction into reality. Yet, it's exactly what a Type 2 civilization would represent. A species that has broken free from the constraints of its home planet and begun to manipulate the very forces of the cosmos to fuel its existence. The Kardashev Scale itself is a simple concept, but it carries profound implications. It's a way of measuring a civilization's technological prowess based on the amount of energy it can harness. Type 1 is planetary, using all the available resources on a single world. Type 2 is stellar, harnessing the energy of an entire star. And Type 3 is galactic, drawing power from a whole galaxy. It's easy to see why Type 2 sits right in the middle as a pivotal point in this theoretical scale. It marks the moment when a civilization leaves behind its planetary infancy and becomes a true player on the cosmic stage. A civilization at this stage wouldn't be limited by the same problems that plague us. Energy scarcity? That's a thing of the past. A Type 2 civilization could expand indefinitely, building infrastructure, colonizing other worlds, and pushing the limits of what's possible without worrying about running out of power. It's the ultimate freedom in a sense. Once you control a star, the opportunities become limitless. And with that kind of energy, they could explore the furthest reaches of their solar system, terraform planets, create massive space habitats, and even begin to look outward toward other stars. But this level of power also hints at something more than just technological achievement. To reach this point, a civilization would have to solve a series of monumental challenges. They'd need to figure out how to build something capable of surrounding a star, like a Dyson sphere or a swarm of solar collectors, without collapsing under its own weight or being torn apart by the forces involved. They'd have to master space travel and construction on a scale that makes our current efforts seem almost laughable. And they'd need the kind of long-term vision and cooperation that we, as a species, often struggle with. The ability to harness a star's energy isn't just about technology. It's about evolution, social, intellectual, and ethical. A Type 2 civilization would likely be more unified, more forward-thinking, and more stable than we can currently imagine. It's also humbling to think about where we stand in comparison. If humanity ever reaches a Type 2 status, it would be after a long and arduous journey. We're still dealing with conflicts over resources, struggling to balance progress with environmental sustainability, and grappling with the complexities of managing our planet's future. Yet, looking up at the stars, the possibility of one day reaching that level of development is tantalizing. It's not just about survival. It's about what we could become. A Type 2 civilization would represent the pinnacle of what humanity could achieve, a future where we no longer fear the fragility of our existence, but embrace the possibilities of mastering the universe around us. But there's also something deeply existential about the idea of a Type 2 civilization. If other civilizations out there have already reached this point, what does that mean for us? The universe is vast and ancient, and the idea that we might not be the only intelligent life has always been a source of fascination and anxiety. If there are Type 2 civilizations out there, they could be observing us, quietly watching as we stumble through our early stages of development, maybe even deciding whether we're worth interacting with. Or perhaps they're so far beyond us that we're not even on their radar, just another primitive species still struggling to control its own destiny. In a way, the Kardashev Scale forces us to think about our future in stark terms. It challenges us to ask where we're headed and what kind of civilization we want to become. Will we be able to harness the energy of our planet and then our star? Or will we fall short, succumbing to the conflicts and limitations that have plagued us throughout history? The concept of a Type 2 civilization isn't just a theoretical exercise. It's a reminder of the potential we hold as a species. It represents a future where we've not only survived but thrived, turning the vast energy of the universe into a force that propels us toward even greater heights. And while that future may seem distant, the very idea of it makes our present struggles feel a little less insurmountable, knowing that the stars themselves could one day be within our reach. The idea of a theoretical megastructure that stretches the limits of human imagination is one of those concepts that forces us to confront just how small we are in the grand scheme of things. It's not simply a bigger building, a taller tower, or even a more sprawling city. Those are still bound by the earthly rules we've always known. When you start thinking about something on the scale of a Dyson Sphere or another similar cosmic scale project, it feels less like an extension of what humans have done and more like an entirely different chapter of existence. It's a structure that would dwarf planets, turning stars into mere power sources, shifting the very nature of how we think about space, engineering, and even life itself. It's not enough to say that these structures are big. They would redefine what big even means. When we imagine large things, we think about the tallest skyscrapers or the longest bridges, but those are still rooted in the familiar. A megastructure that can encompass a star or function on a system-wide scale is operating in a realm where size is no longer the limiting factor. It's like trying to explain infinity to someone who's only ever counted to 10. The sheer scale of it requires us to think in ways we're not naturally inclined to. Everything about it, from the engineering to the logistics, to the materials, and even to the purpose, is a stretch beyond what our current minds can fully grasp. But that's exactly what makes it so compelling. The very idea that such a structure could exist is like a dare to human ingenuity. Can we even imagine how to begin? What materials could survive the extreme conditions of being close to a star, where radiation, gravity, and heat combine to create an environment that would obliterate most of what we know? Even if we figured out how to build something that could withstand these forces, how would we get the resources and the manpower to construct something on this unfathomable scale? It's not just a technical question, but an existential one, pushing us to think far beyond the confines of Earth and even beyond the limits of what we know about physics. There's something both awe-inspiring and humbling in the realization that these megastructures, though theoretical, are within the realm of possibility. They represent the outer edge of human ambition, the point where we stop thinking about what's practical and start embracing what's audacious. Imagine the kind of cooperation it would take, the global or even interplanetary effort needed to pull something like this off. Nations would have to set aside their differences. Perhaps entire species, if intelligent life elsewhere exists, might have to collaborate. It's a vision of the future that feels far removed from the world we know. But it's also a vision that sparks the imagination, opening up possibilities we hadn't dared to consider. And yet, despite how overwhelming it sounds, the thought of these megastructures also carries a certain hope. If we could build something like this, it would mean that we had solved some of the biggest challenges we face today. We'd have figured out how to gather enough energy, mastered space travel to an unimaginable degree, and created technologies that are still pure science fiction. These structures aren't just about size. They're about transcending limitations. They signal a future where humanity isn't restricted by the scarcity of resources, the dangers of space, or the fragility of life on a single planet. In that sense, they're a symbol of what we could achieve if we dared to think big enough. But thinking about a structure that could stretch across an entire solar system, or one that could encapsulate a star, does something else, too. It makes us confront our current limitations in a way that's almost uncomfortable. We're still so focused on our planet, so tied to the small dramas of daily life, that contemplating something on this scale feels almost alien. The challenges we face, global warming, energy shortages, political conflicts, seem petty in comparison. If we could build something this vast, it would mean that we had moved beyond all of that, leaving behind the struggles of a single world to embrace the possibilities of the stars. Yet the human element remains. These theoretical megastructures wouldn't just be products of advanced technology. They'd be expressions of human desire, creativity, and ambition. They would be the ultimate proof of our ability to dream beyond what we know, to push the boundaries of possibility, even when the obstacles seem insurmountable. They represent what's possible when we stop asking if something can be done and start asking how far we can take it. It's the kind of thinking that has always driven humanity forward, looking at the moon, the planets, and the stars and asking, what if? In a way, The concept of a megastructure is less about the structure itself and more about the mindset it represents. It's a future where we no longer view the universe as something that happens to us, but as something we can shape, mold, and build within. It stretches the limits of imagination, not just because of its size, but because it shows us that even the wildest dreams might one day be within reach. And for all its theoretical complexity, at the heart of it is a simple truth. This is what it means to be human, to look at the impossible and wonder how we can make it real. The world of engineering and technology stands at a precipice, where extraordinary advancements are shadowed by equally formidable challenges. Engineers today, with all their skills and innovations, often find themselves walking a fine line between what is theoretically possible and what is practically achievable. Our technological ambitions stretch across vast domains, from building cities that can withstand nature's growing fury to creating machines that blur the line between human and artificial intelligence. But as we push these boundaries, we encounter the limitations of our current capabilities, making the pursuit of these grand visions far more complex than it might seem. At the heart of these challenges is the material world itself. The tools and materials we use, whether metals, polymers, or composites, can only be pushed so far before their inherent properties start to break down. Buildings can be made taller, but with every additional story comes the question of how to support that weight without compromising stability. Our technology to enhance strength has come far, but nature itself often imposes restrictions. One need only look at the failures of bridges, which, despite careful design, sometimes buckle under forces we cannot fully anticipate. It's the human element of uncertainty, a reminder that no matter how advanced our calculations, nature may always have one more surprise in store. Energy also plays a central role in shaping the boundaries of what we can achieve. As much as we dream of clean, limitless power, the reality is that we are still deeply reliant on technologies that, while powerful, have limitations. Solar panels, wind turbines, and batteries are remarkable, but they struggle to meet the continuous demands of an energy-hungry world. And then there's the issue of scale. Even if a technology works brilliantly in a laboratory setting or on a small scale, expanding it to power entire cities or countries introduces complexities that are not easily solved. The dream of transitioning to sustainable energy, while closer than ever, is still a massive undertaking that requires far more refined solutions than what we currently have. Artificial intelligence, too, though promising, presents profound challenges. It's easy to marvel at the capabilities of AI systems that can process information faster than any human could dream. But the closer we come to relying on these technologies, the more we confront their fragility. AI systems are not immune to bias, errors, or limitations. They process the data we feed them, and that data is far from perfect. As we integrate AI into more critical roles in healthcare, transportation, and security, the weight of responsibility becomes clearer. Mistakes made by machines may not have the emotional weight of human error, but they can be just as devastating, and unlike humans, machines can repeat their mistakes on a massive, unprecedented scale if not properly checked. In space exploration, the horizon seems almost endless, but the practical challenges of sending humans to Mars or beyond are daunting. Rockets, as they stand now, are marvels of human ingenuity, but they are also primitive in their reliance on brute force and massive energy consumption. We have yet to develop propulsion systems that can carry us to the stars in a way that is both efficient and sustainable. It's not just about getting there, though. Once we arrive, the challenges of surviving in hostile environments remain largely unsolved. The psychological toll of isolation, the dangers of radiation, and the scarcity of resources are reminders that even the best technologies are often tested in the face of the unknown. As our cities grow more complex, they become both marvels of human achievement and ticking time bombs. The sprawling infrastructure that supports modern life, roads, bridges, electrical grids, water systems, was often built with a different time and mindset in mind. Now, many of these systems are being stretched to their breaking points, not just by the pressure of growing populations, but also by the unpredictability of a changing climate. The task of upgrading, maintaining, or overhauling these systems requires not only technological solutions but political will, coordination, and substantial investment, all of which are often harder to come by than the technology itself. In medicine, we've seen incredible advances with technology like gene editing and advanced prosthetics, but there remain profound limits on how far we can go in eradicating diseases, regenerating damaged organs, or understanding the complexity of the human brain. The body is a delicate ecosystem, one that we have learned a lot about, but still understand only partially. Attempts to treat one area can have unforeseen consequences elsewhere, reminding us of the balance we must maintain between innovation and caution. Medical technology continues to expand the frontiers of what's possible, but it's also constrained by ethical dilemmas and the limits of our current understanding. The greatest challenge might not be the individual technological hurdles, but the interconnectedness of them all. No single breakthrough exists in isolation. Each achievement opens up new questions, exposes new vulnerabilities, and often requires other technologies to evolve in tandem. In a world where systems are deeply integrated, where cities, economies, and even entire societies rely on layers of technology working flawlessly together, the margin for error becomes thinner and thinner. A flaw in one part of the system can ripple through, affecting everything from personal data security to global economies. In the end, it is not the machines, algorithms, or buildings that truly define our technological landscape, but the people behind them. Engineers, scientists, and visionaries are continually pushing forward, but they are also humans who make mistakes, face limitations, and are driven by the same uncertainties that affect all of us. The beauty and challenge of engineering today lie in its ambition, its willingness to tackle the impossible, but also in the realization that, despite all our advancements, we are still learning to navigate a world that is more complex and interconnected than any technology we've ever created. As we gaze into the cosmos, searching for signs of life beyond our world, we are met with the vast silence of space, a silence that feels almost too deep for comfort. Yet, that silence itself raises profound questions about the existence of advanced alien civilizations. The universe is staggeringly old, filled with billions of stars, many of them surrounded by planets that could potentially harbor life. With such an abundance of cosmic real estate, the absence of clear evidence for intelligent life forces us to confront the possibility that either we are alone, or we simply have not yet figured out how to recognize those other civilizations. It's tempting to believe that life, particularly intelligent life, must be common. After all, Earth teems with life, and we've proven that life can adapt to environments as extreme as the deep ocean trenches and scorching volcanic vents. But what if the journey from simple life to technologically advanced civilizations is rarer than we think? The conditions that led to the rise of humanity, from the right distance from our sun to the delicate balance of our atmosphere, may not be easily replicated elsewhere. Maybe there are countless worlds where life exists, but never quite develops the intelligence or technology to reach beyond their own planets. However, there's another, more unsettling question. What if advanced civilizations do exist, but they are choosing not to communicate with us? The idea that an alien race might observe us from a distance, deciding that we are not yet ready for contact, brings a deeply human anxiety to the forefront. It echoes our own concerns about the unknown, about whether we would welcome such a civilization with open arms, or whether we would react with fear and hostility. Perhaps they are waiting for us to pass some threshold of technological or ethical development before revealing themselves. It raises the uncomfortable possibility that, despite all our advancements, we are still seen as primitive in the grander scale of the universe. Then again, it's possible that these civilizations are simply too far ahead of us to care. If they are millions or even billions of years more advanced, our existence might be as insignificant to them as bacteria are to us. They may have long since transcended the need for physical forms, traveling the cosmos in ways we cannot begin to comprehend. To them, reaching out to a fledgling species like ours might be as irrelevant as trying to communicate with the atoms that make up our bodies. The very concept of communication may be something we do not fully understand, limited by our human perceptions and technological capabilities. But the questions don't stop there. What if there's a reason why we haven't found them? Because they aren't there to be found. The idea that advanced civilizations may eventually destroy themselves, whether through war, environmental collapse, or technological missteps, looms large. It forces us to confront our own future, to wonder whether we, too, might fall victim to the same forces that could have wiped out others. The more we advance, the more we develop weapons and technologies capable of eradicating life on a planetary scale, the more we begin to wonder if intelligent life is destined to be short-lived. This possibility casts a shadow over our search for alien life, suggesting that perhaps the silence of the stars is not a mystery, but a warning. Still, it's hard to escape the feeling that somewhere, out there, others are asking the same questions. They may look up at their sky, wondering if there is life beyond their world, just as we do. They might be driven by curiosity, the desire to explore, and the same existential loneliness that drives us. There's something deeply human about this shared sense of searching, of not wanting to be alone in the vastness of space. And perhaps this very human desire is what keeps us looking, even when the odds seem daunting, and the silence grows more deafening. The universe is ancient, and the possibilities for life seem endless. But with every new piece of technology we launch into space, with every signal we send out into the void, we are reminded of how little we truly know. The search for advanced civilizations forces us to reflect on our own existence, to question what it means to be intelligent, and to consider the fragility of our place in the cosmos. And as we wait, listening for a signal, watching for a sign, we're left with a feeling that the answers, if they ever come, may be far stranger than we can imagine. The way we think about energy is beginning to shift in ways that could fundamentally alter the trajectory of human civilization. As the world's population grows and our demand for energy intensifies, we find ourselves standing at a crossroads. For centuries, humanity has relied on fossil fuels to power its progress, but the cost of this reliance is becoming impossible to ignore. The environmental toll, the geopolitical tensions surrounding oil, the finite nature of these resources, all of it is pushing us toward a future that demands something more sustainable, something that won't simply burn itself out or choke the planet. Yet, the path forward is not without its complexities. The idea of renewable energy once felt like a distant hope, a luxury that could only supplement our primary sources. But now, technologies like solar, wind, and geothermal are no longer fringe experiments. They're increasingly central to the conversation. Solar panels, once seen as inefficient and prohibitively expensive, are now being developed with extraordinary efficiency. It's not just a matter of catching the sun's rays anymore, but finding ways to store and distribute that energy in a way that could sustain entire cities. As these technologies evolve, the question becomes whether we can scale them fast enough to meet global needs. The promise is there, but the challenge remains colossal. To transform how we produce, store, and transmit energy on a scale that humanity has never before attempted. At the same time, nuclear fusion, long the holy grail of energy research, hovers on the edge of becoming a reality. Unlike nuclear fission, which leaves behind radioactive waste, fusion promises a nearly limitless supply of clean energy, with nothing more dangerous than helium as a byproduct. The science has always been sound, but controlling the process has been a monumental task. It's the sort of challenge that has drawn in some of the brightest minds, fueled by the dream of an energy source that could power the planet for centuries without the same devastating consequences of fossil fuels. The thought of tapping into the same process that powers the stars, harnessing it here on Earth, is almost too transformative to fully comprehend. If successful, fusion could change everything. Not just how we consume energy, but how we live, work, and interact with the planet's resources. However, energy isn't just about the big breakthroughs. It's also about the small innovations that ripple out into every corner of life. Smart grids, for example, are already beginning to revolutionize how we distribute energy, allowing for a more dynamic, flexible approach to supply and demand. These systems, which intelligently balance loads, can make renewable sources like solar and wind more viable by compensating for their variability. This means that instead of simply producing energy in large, centralized power plants, energy can be decentralized, generated in neighborhoods or even individual homes, and then efficiently shared. The human element here is significant. This decentralization could fundamentally alter not just the economy but how communities interact with energy. Instead of relying on distant power companies, people may find themselves producing and managing their own energy, a shift that could lead to more autonomy and sustainability at the local level. Yet, for all the technological promise, there's also the human challenge of how we adapt to these changes. The transition to new forms of energy is not just a matter of switching technologies. It's a cultural and societal shift. There are industries built on fossil fuels, economies propped up by oil, and millions of jobs tied to these outdated systems. A future powered by renewable energy means more than technological innovation. It means retraining workers, rethinking economic models, and facing resistance from those who fear the loss of stability and livelihoods. It's easy to talk about a greener future, but it's harder to reconcile that vision with the realities faced by those whose lives are tied to the old ways. Moreover, there's the question of who will control this new energy future. The technology to produce clean energy is increasingly available, but the distribution of resources and infrastructure remains uneven. Wealthier nations are pushing ahead with clean energy investments, while many parts of the developing world are still struggling to provide consistent power to their populations. The future of energy consumption may well depend on whether we can bridge these gaps, ensuring that the benefits of new technologies are shared globally and not just concentrated in areas that can afford the transition. This adds a deeply human dimension to the energy question, one that's as much about fairness and equity as it is about science and engineering. In the background of all these developments, there's the growing awareness of energy efficiency. The less energy we waste, the less we'll need to produce. This isn't a glamorous part of the energy conversation, but it's crucial. Advances in everything from home insulation to electric vehicles to more efficient industrial processes are quietly transforming how much energy we consume in the first place. While we look toward the promise of clean energy sources, we're also learning how to use less energy overall, shrinking our footprint in ways that could have a profound impact on future generations. The future of humanity's energy consumption could unfold in any number of directions, but what's clear is that we are at a critical point. The decisions made now, the investments in technology, infrastructure, and policy, will set the course for decades, perhaps centuries to come. Whether it's through solar farms, fusion reactors, smart grids, or simply learning to consume less, the path ahead will not be straightforward. It's filled with promise and peril, ambition and uncertainty, and at its core, it's a deeply human challenge, one that will define not just how we live, but whether we can continue to thrive on this planet. Imagining the largest structure ever conceived in human history stretches the boundaries of what we think is possible, not just in terms of engineering, but also in terms of human ambition. It forces us to reconsider what kind of projects we are truly capable of, especially in an age where technology and innovation are advancing at a dizzying pace. The idea of creating something so vast that it dwarfs every building, bridge, and monument we've ever constructed is daunting, yet it also speaks to a deeply ingrained human desire to leave a mark, to create something that stands the test of time, something that could echo through the ages as a testament to our ingenuity and perseverance. One vision that has captivated imaginations is the concept of a space elevator. This would be a structure so immense that it could connect Earth to space, reaching beyond the clouds, through the atmosphere, and into low Earth orbit. The engineering challenges are staggering. To build a cable stretching tens of thousands of kilometers into space requires materials that are still the stuff of science fiction, like carbon nanotubes or graphene, substances strong enough to withstand the unimaginable forces involved. The very idea of constructing such a structure raises questions not just about physical limits, but about human endurance, about whether we could coordinate such an endeavor over the many decades it would take to complete. And yet, the rewards would be immense. A space elevator would revolutionize how we access space, making it far cheaper and more efficient to transport people and cargo beyond our planet's grasp. It would transform space travel from a rare and costly event into something routine, possibly unlocking a new era of exploration and even colonization. But the space elevator is only one of many visions for a colossal structure. Another idea that has gained traction is the concept of a Dyson Sphere, a megastructure designed to encircle a star and capture its energy output. If humanity were ever to build such a thing, it would be on a scale so vast that it would make even the most ambitious space stations or planetary bases seem trivial by comparison. The amount of raw material needed alone boggles the mind. It would likely require mining entire asteroids or even moons to gather enough resources. Such a structure would tap into a nearly limitless supply of energy, but it raises profound questions about what kind of civilization we would need to become to even attempt such a feat. It's not just a matter of technology. It's about whether we could organize ourselves on a scale that spans centuries, with a common purpose that unites generations in the pursuit of a goal so far-reaching that it stretches the boundaries of what it means to be human. And yet, even within our own planet, there are concepts that would dwarf anything we've built so far. Some have proposed creating artificial cities that float in the oceans, sprawling metropolises capable of housing millions of people, with self-sustaining ecosystems that could provide for all their needs. These ocean cities would not only represent the largest physical structures ever built, but they would also signify a radical rethinking of how we live and interact with the environment. As the climate crisis worsens, the need for adaptable, resilient structures will grow. These cities could be a response to rising sea levels, providing humanity with a way to survive on an increasingly unpredictable planet. But building such cities would require innovations in energy production, resource management, and construction techniques that we are only beginning to explore. More than that, it would require a shift in how we see ourselves, not just as inhabitants of fixed landmasses, but as a species capable of thriving in even the most challenging environments. Even more down to earth, some of the largest engineering feats ever conceived involve tackling global-scale issues like climate change. The idea of constructing enormous carbon capture systems to scrub the atmosphere of excess CO2 has been floated as one potential solution to the climate crisis. These machines, if built at a sufficient scale, would need to operate continuously, pulling billions of tons of carbon from the air to prevent catastrophic warming. This isn't about building a single, towering structure, but a global network of machines working in unison, a kind of artificial forest spread across continents, quietly working to save the planet. The logistics of such an undertaking are staggering, requiring not just technological breakthroughs, but unprecedented international cooperation and political will. All of these visions, whether reaching for the stars or grounded in our own changing environment, share a common thread. They push the boundaries of what we believe is possible. They raise questions about our capabilities, but also about our commitment to the future. It's easy to be overwhelmed by the scale of these projects, to feel small in the face of such immense ideas. But there is something deeply human in our desire to dream on such a grand scale, to envision structures that are not just for us, but for the generations that will come after. These ideas represent more than just technological achievements. They are a reflection of our hopes, our fears, and our endless curiosity about what lies beyond the next horizon. As we stand at the edge of this new era, the question isn't whether we can build the largest structure in human history. It's whether we will choose to. Because in the end, the true challenge isn't just in the engineering or the materials. It's in the willingness to imagine a future bigger than ourselves, to work toward a goal that may take lifetimes to achieve, and to embrace the unknown in pursuit of something extraordinary. The Kardashev Scale suggests that a Type 2 civilization could harness the full energy of its star, a feat achievable through a Dyson sphere. This concept ties into the Fermi Paradox, which asks why we haven't encountered such advanced civilizations if they exist. One possible answer is that they may be using Dyson spheres, detectable through their unique infrared technosignatures. Organizations like SETI actively search for these signs of alien life. While Dyson spheres are the most well-known concept, alternatives like Dyson swarms also exist, though both present massive challenges in terms of materials and engineering. If realized, these structures could revolutionize humanity's future, offering energy dominance, aiding space colonization, and fulfilling the ambitious visions explored in science fiction. The Kardashev Scale is a method of classifying civilizations based on their energy consumption and control over resources, developed by Soviet astrophysicist Nikolai Kardashev in 1964. It's a way of imagining what highly advanced civilizations might look like, offering a framework to think about humanity's future in a cosmic context. The scale starts at Type 1, which describes a civilization that can harness and utilize all the energy available on its home planet. Humanity, right now, isn't even at this stage. Our global energy consumption is still just a fraction of what the Earth is capable of providing through natural resources like solar, geothermal, and wind power. Reaching Type 1 would require overcoming political, environmental, and technological hurdles that seem almost insurmountable today. But it's a level that would mark a civilization's complete mastery over the planet, where energy shortages, as we know them, would no longer exist. As we imagine a civilization moving beyond its planet, it enters the realm of Type 2. At this stage, a species would have to harness the total energy output of its home star. This concept is often associated with the idea of a Dyson sphere, a theoretical megastructure that could capture all the energy emitted by a star. The leap from Type 1 to Type 2 is enormous and challenges our current technological imagination. It's not just about the engineering challenge of building something like a Dyson sphere. It's also about the profound societal changes that would be required. Such a civilization would have to be unified and technologically advanced to a degree that goes beyond anything we've ever experienced. They would have to be explorers by necessity, moving beyond their own planet and colonizing other worlds in their solar system, driven not just by survival but by curiosity and an ever-increasing demand for energy. Beyond this, there's Type 3, where a civilization controls energy at a galactic scale, utilizing the power of entire star systems across the galaxy. This level seems almost mythical, but it forces us to imagine a civilization so advanced that they've become interstellar, perhaps mastering faster than light travel, or bending space-time itself to their will. Such civilizations would likely look incomprehensible to us, operating on a scale and timeline so vast that they might perceive planets, stars, or even galaxies in the same way we view grains of sand. This level of development implies not only technological mastery, but possibly some fundamental changes in how such beings might exist. At this point, they may not even resemble biological life forms as we know them. They could be artificial intelligences or post-biological entities, integrated with their machines or dispersed across star systems as digital consciousness. But as humans, it's difficult to fathom what social dynamics, ethics, or motivations such civilizations would have. Our history is one of struggle, conflict, cooperation, and survival. Would these advanced civilizations still carry traces of their evolutionary origins? Would they still be competitive, expansionist, or materialistic, or would they evolve beyond such needs? Or perhaps they would have reached such a degree of wisdom and understanding that their societies operate in harmony, driven by higher purposes we can't even comprehend. The Kardashev Scale, for all its focus on energy, also invites speculation on what it means to be a civilization at different stages of growth. It leaves room for questions not only about technological progress, but also about the evolution of culture, morality, and identity as species expand their horizons across the stars. For humanity, the Kardashev Scale isn't just a measure of energy use. It's a roadmap for the future, one that prompts reflection on the challenges we face as a species today. It's a reminder of our potential, of what we might become if we survive long enough to evolve beyond the narrow scope of our current limitations. The idea of advancing along the scale forces us to confront the deeper question of how we should manage the resources we have now, how we address global crises like climate change, and whether we can overcome our divisions to reach a more unified and sustainable way of living. In the end, the Kardashev Scale paints a picture of a universe filled with infinite possibilities, but also asks whether humanity can learn to handle the responsibility of such immense power and knowledge without losing itself in the process. The Fermi Paradox is the unsettling contradiction between the high probability that intelligent extraterrestrial life exists somewhere in the universe and the lack of evidence or contact with any such civilizations. The paradox takes its name from physicist Enrico Fermi, who famously asked, "Where is everybody?" during a casual conversation about the likelihood of advanced extraterrestrial life. His question gets at something profoundly human: the innate curiosity and desire to know whether we are alone in the vastness of the cosmos. When we look up at the night sky, filled with billions of stars and planets, it seems almost absurd to think that Earth is the only place where life has emerged. And yet, despite decades of searching, through radio signals, space exploration, and sophisticated astronomical surveys, we've found no conclusive proof that anyone else is out there. The paradox is as much a reflection of human wonder as it is of human frustration. On one hand, there's the intoxicating possibility that intelligent life is abundant, perhaps even far more advanced than we are. On the other hand, there's an eerie silence that suggests we might be alone, or that something prevents civilizations from reaching out to one another. The paradox makes us question not just the cosmos, but our own place within it. If intelligent life is common, why haven't we seen signs of it? There are countless stars older than the sun, with planets that could have harbored life for billions of years. If even a fraction of those planets produced intelligent species, some of them should have developed the technology for interstellar communication or travel. Perhaps, we think, we should have been visited, or at least noticed some kind of technological footprint from these civilizations. But nothing. The silence persists. One of the unsettling implications of the Fermi Paradox is that it forces us to confront the fragility of civilizations. Could it be that advanced civilizations inevitably destroy themselves before they are capable of reaching out to the stars? It's a thought that resonates deeply in a world where humanity itself struggles with existential risks, nuclear weapons, climate change, and now artificial intelligence. Maybe civilizations, no matter how technologically advanced, are always just one step away from catastrophe. The same ingenuity that allows a species to dominate its planet might also contain the seeds of its destruction. This possibility injects a sobering human element into the paradox. If the silence in the cosmos is because civilizations tend to annihilate themselves, what does that mean for us? Are we destined to follow the same path? Or can we find a way to break the cycle? There are, of course, other possibilities. Perhaps extraterrestrial civilizations are out there, but they're deliberately avoiding contact with us. Some theories suggest that advanced species might practice a form of cosmic quarantine, leaving less developed civilizations like ours to evolve naturally without interference. This is akin to how we might treat uncontacted tribes on Earth, watching from a distance, but not intervening. Or maybe they communicate in ways we don't yet understand. using technology so far beyond our own that we're incapable of detecting it. From our current standpoint, our search methods might seem laughably primitive to an advanced civilization that has moved beyond radio waves and telescopes. The paradox also forces us to think about the limits of our own imagination and perception. We tend to assume that alien life, if it exists, would be like us, technological, curious, and perhaps eager to explore. But what if they're fundamentally different? What if their understanding of existence or their desires are so alien that contact with us isn't even a consideration? Or, perhaps even more disturbing, what if life itself is rare, and Earth is an almost impossible anomaly, a precious island of consciousness in an otherwise indifferent universe? The Fermi Paradox doesn't offer answers, only questions. It reflects the deep yearning of humanity to understand its place in the cosmos, while also revealing the limitations of our knowledge. We are still such a young species, confined to one planet, only beginning to stretch our senses into the vastness of space. The paradox is a mirror that forces us to confront our own significance, or lack thereof. It taps into the existential fear that maybe, despite all our efforts to understand and explore, we're simply not ready or capable of finding others like us. Or worse, that no one is out there at all. The idea of alien civilizations constructing Dyson spheres, massive structures designed to harness the full energy output of a star, is one of the most intriguing concepts when we try to imagine the capabilities of advanced life forms. It's a notion that pushes the boundaries of what we consider possible, and it stems from our own fundamental needs as a species. As we continue to grow, we face constant challenges in securing enough energy to sustain our civilization. So, it makes sense that when we think about extraterrestrial civilizations, we project our own desires onto them. The need for more energy, more resources, more space. A Dyson sphere represents the ultimate solution to such needs, a way for a civilization to capture the vast energy of its star and power everything from planetary systems to colossal megastructures. But imagining alien civilizations building such an immense structure is more than just a thought experiment about technology. It's a reflection of how we view progress and survival. For us, energy is a limitation. It's what drives economies, shapes geopolitics, and influences how we live our daily lives. The idea that a civilization might bypass these constraints by building something as monumental as a Dyson sphere feels almost utopian, or perhaps dystopian, depending on how you look at it. The sheer ambition of constructing such a thing says something about the kind of society that could even entertain the idea. They wouldn't just be technologically advanced. They would have to be organized, focused, and capable of long-term planning on a scale that we, as humans, can barely fathom. Can you imagine a society so unified and advanced that it could commit the time, resources, and ingenuity to wrap a star in a massive energy-capturing structure? It challenges our perceptions of what a civilization might look like when it has mastered not just its planet but its solar system. But what kind of beings would create such a structure? What would motivate them to go to such extremes? We often think about energy needs in the context of survival, securing enough to ensure the continuation of a species. However, alien civilizations building Dyson spheres might be doing so for reasons that go far beyond survival. Maybe they're driven by the pursuit of knowledge, exploration, or even artistic expression, using the energy to power technologies or experiences we can't even begin to imagine. Or perhaps they've evolved in such a way that energy consumption itself becomes a kind of existential goal, fueling vast virtual worlds, artificial intelligences, or machines that have long since replaced biological life. In this sense, Dyson spheres could represent not just technological power but a shift in what it means to exist as a civilization. Then there's the human question of what happens after such a project is completed. Would a civilization be content with the endless energy at its disposal, or would it only drive them to seek more? Dyson spheres might be the first step in a long process of galactic colonization, where energy is no longer a barrier and the civilization begins to spread its influence across the stars. Or, conversely, it could mark the end of their outward expansion. With such a limitless source of power, they might turn inward, focusing on perfecting their own society or exploring the inner realms of existence rather than physical space. Either way, the completion of a Dyson sphere suggests a turning point in the history of a civilization, one that we can only speculate about with our limited perspective. On a more personal level, thinking about alien civilizations and Dyson spheres raises questions about our own future. If we ever discover evidence of a Dyson sphere, say through an odd dimming of a distant star or some other technological signature, How would that change how we see ourselves? It would be proof that another civilization has not only survived long enough to reach such an advanced stage, but has also managed to avoid the pitfalls that threaten us today. It would serve as a reminder of what we could become, but also of the challenges we face. Are we capable of organizing ourselves to the degree that such monumental feats would require? Or are we destined to remain limited by our own divisions and short-term thinking? A Dyson sphere, far from being just a piece of alien engineering, is a symbol of both potential and peril, and it reflects the tension between what we are and what we might one day become. If we survive long enough to reach for the stars, SETI, or the search for extraterrestrial intelligence, represents humanity's attempt to answer one of its oldest questions. Are we alone in the universe? For decades, SETI has primarily focused on detecting signals, radio waves, or other forms of electromagnetic communication that could indicate the presence of intelligent life elsewhere in the cosmos. But as our understanding of technology and the universe has expanded, so too has the scope of SETI's search. The concept of Dyson spheres has become an exciting addition to this hunt. Instead of just listening for deliberate messages sent across the stars, SETI now also looks for indirect signs of advanced civilizations, like the massive energy signatures a Dyson sphere would produce. Dyson spheres are hypothetical, but the reasoning behind looking for them is grounded in something very human: practicality. If an alien civilization has grown powerful enough to need or build a structure capable of harvesting the entire energy output of a star, that's not just science fiction. It's a sign of progress, ambition, and survival. From a SETI perspective, a Dyson sphere would be like a beacon, an unintentional signal. We might never hear a message from such a civilization, but we could still detect their presence through the unique way their structure blocks or alters the light from their star. Instead of searching for radio waves, SETI is also searching for anomalies in the way stars behave, looking for those that dim in irregular, significant ways, something you'd expect if a Dyson sphere were orbiting around it. The search for Dyson spheres feels more tangible in some ways than listening for alien signals. Radio waves could easily be missed, especially if an alien civilization is using communication methods beyond our current technology. But a Dyson sphere, by its very nature, would leave a large footprint. It taps into the idea that even if advanced civilizations aren't trying to communicate, they can't hide their existence once they start manipulating their stars. That appeals to a deep, human sense of curiosity and exploration. It's like looking for the cosmic equivalent of city lights at night, evidence that, somewhere out there, intelligent beings are working, building, thriving. Yet the search for such megastructures is inherently uncertain. If we don't find any, what does that mean? Are Dyson spheres simply too ambitious, even for advanced alien civilizations? Does it suggest that such civilizations might have found more efficient ways of harvesting energy, ways we can't even begin to imagine? Or worse, does it point to a more unsettling idea, that perhaps civilizations don't last long enough to reach such heights? The failure to find Dyson spheres, or any evidence of advanced civilizations, so far forces us to confront our own fragility. Are we capable of growing to the point where we'll one day be detectable in the cosmos by someone else's search? For the scientists working at SETI, the search for Dyson spheres and other advanced signs of life is a humbling experience. They know they're looking for something monumental, something that would fundamentally alter our understanding of life and intelligence in the universe. But at the same time, the absence of evidence is equally profound. It raises more questions than it answers, reminding us that the universe is vast, and we are just beginning to stretch our reach. Every star that SETI examines for Dyson spheres, every strange dimming event or stellar anomaly that turns out to be natural rather than artificial, doesn't just represent a scientific puzzle. It represents the hopes and dreams of people who wonder whether the human species is part of a much larger story, or whether we are the anomaly, the outlier in a quiet, empty universe. In the end, the search for Dyson spheres within SETI is about more than just finding aliens. It's about understanding what's possible in the universe. It's about imagining what civilizations might become when they break free of the constraints that bind us here on Earth. Searching for these megastructures forces us to think about energy, technology, and survival in ways that make us question our own future. And maybe, just maybe, it will one day give us a glimpse of what humanity itself could achieve if we survive long enough to reach for the stars and build our own megastructures. But until then, SETI continues its quiet, patient search, one star at a time. The search for alien life has always been driven by the hope that somewhere out there, another form of intelligence exists, trying to communicate or leaving traces of its existence. Over the years, The concept of technosignatures has become a significant focus in this search, shifting the approach from hoping for deliberate contact to looking for any signs that technology has left behind. Technosignatures refer to the indirect evidence of technological activity, the fingerprints of a civilization that might not even know we exist. These are things that could be universal, such as pollution in a planet's atmosphere, unusual radio signals, artificial lights, or vast structures built around stars. It's the idea that, no matter where they come from or how they think, intelligent species would need technology to survive and thrive, and that technology would leave detectable marks on their environment. Humans, whether we realize it or not, are already leaving technosignatures of our own. Satellites orbiting Earth, the radio waves we've been sending out for nearly a century, the emissions from our industries. These are all signs that someone, or something, is living on this planet. If an alien civilization were looking for us, they wouldn't need to wait for us to send a message. They could detect us simply by observing these subtle but unmistakable signs of technology. This realization, that intelligent life leaves traces even when it's not trying to be found, fuels the search for technosignatures. It taps into the very human instinct to explore, to search for signs of life in places we can't yet physically reach, and to piece together the mysteries of the universe from afar. The beauty of searching for technosignatures is that it expands the definition of what it means to find alien life. We're not just looking for radio waves or direct contact anymore. Instead, we're looking for any hint that life has moved beyond its natural environment and started shaping it. Maybe it's a civilization that has mastered interstellar travel and left trails of energy emissions in space. Maybe it's a society that has industrialized to the point where its pollution has altered its planet's atmosphere. Or maybe it's something even more advanced, so much so that the signs are harder to recognize because we don't yet have the technology or the perspective to understand them. But this search isn't just about science or technology, it's about what it says about us as humans. We're searching for signs that someone else has made it, that they've survived the challenges of their environment and their development, and that they've continued to evolve. There's a hope that comes with looking for technosignatures, a hope that intelligent life can outlast the problems we face here on Earth, like climate change, war, and the limits of resources. Finding technosignatures would be a profound reassurance that civilizations can survive their growing pains and reach levels of technological mastery without self-destruction. At the same time, it's a reminder of how delicate life is. If we don't find any technosignatures, we might have to confront the possibility that the lifespan of advanced civilizations is short, that they don't survive long enough to leave behind lasting marks. What's fascinating about technosignatures is the sheer variety of what we could find. They don't have to be intentional, like a message broadcast into space. Instead, they might be as simple as the strange dimming of a star, which could suggest a megastructure like a Dyson sphere. Or it could be odd fluctuations in a planet's atmosphere, hinting at industrial activity. The possibilities are as vast as our imagination, and each discovery, whether it's a false alarm or a true signal, gets us closer to understanding the nature of technological life in the universe. For many people, the search for technosignatures is about connection. We want to know that, in this enormous universe, we aren't the only ones who've developed the capacity to shape our world and beyond. It's a search for kinship, for the understanding that life, intelligence, and innovation aren't unique to Earth. At its heart, the search for technosignatures is driven by the hope that there is more out there. More civilizations, more stories, more futures than just the one we know. And in the process of looking for these signs, we also come to reflect on our own existence. The marks we're leaving on our planet, the way we might be perceived by others, and what kind of legacy we're building as we advance through our own technological age. Whether we find technosignatures or not, the search itself pushes us to think deeply about what it means to be a civilization and what it means to be human. The idea of detecting a Dyson sphere through infrared radiation is both simple and profound, resting on the fundamental laws of thermodynamics. If an advanced alien civilization were to build a Dyson sphere, a massive structure surrounding a star to capture its energy, there's no way they could avoid the inevitable heat generated by such an enormous operation. Just as any machine or living being gives off waste heat, so too would a Dyson sphere, radiating it in the form of infrared light. This waste heat would be the key clue, a subtle yet significant fingerprint that SETI and other astronomers are searching for, as it might be the best way to detect such megastructures. For scientists, the beauty of infrared detection lies in its universality. Any advanced civilization, regardless of how sophisticated their technology might be, would have to contend with heat. This makes infrared a kind of cosmic giveaway, a signal that can't be hidden no matter how advanced or elusive the civilization might be. Even if a Dyson sphere completely blocked out the light of its star, causing the star to seem dimmer or even invisible to us in visible wavelengths, it would still emit infrared radiation, glowing faintly from the sheer heat of the star's energy being absorbed and then re-radiated by the sphere. In this way, astronomers looking for Dyson spheres are like detectives, scanning the sky not for what we can see with our eyes, but for the invisible warmth of a civilization's energy usage. The search for these infrared signatures is deeply connected to human intuition about survival and progress. We ourselves are constantly seeking new sources of energy, and as our technology develops, we require more and more of it. So when we think about alien civilizations, we project our own experience onto them. The idea that as they grow, their energy needs would increase exponentially, eventually leading them to construct something like a Dyson sphere. But while the concept of harvesting a star's energy might seem outlandish, the search for its infrared signature is grounded in the same principles that govern how we detect heat here on Earth. Whether it's a forest fire, a power plant, or an overheating machine, infrared radiation tells us something fundamental is happening. And that idea holds true on a galactic scale as well. In many ways, the search for Dyson spheres through infrared detection is not just about finding aliens. It's about imagining what a civilization might look like at its most evolved stage. What would it mean for a species to be able to capture and use the energy of an entire star? What would life be like under a Dyson sphere, where the energy needs of entire planets could be met with ease? For us, such a future feels almost utopian, a dream of unlimited resources that would free humanity from the constraints of scarcity. But it's also humbling. The civilizations we're searching for might have found solutions to problems we are only beginning to grapple with. Their mastery over energy might reflect a level of social and technological advancement that makes our own efforts feel small by comparison. There's also something deeply speculative and philosophical about this search. What if we never find any Dyson spheres? Does that mean civilizations don't reach that level of development, or that they find alternative ways to harness energy? Or perhaps the absence of Dyson spheres is a warning, an indication that even advanced civilizations face limits, whether self-imposed or natural, that prevent them from expanding in such dramatic ways. The search for infrared signatures, then, becomes a way to probe the possibilities of not just alien life, but the very nature of technological progress. On a personal level, the idea of finding a Dyson sphere through infrared detection connects to our most basic human desire for connection. If we were to detect such a structure, it would be proof that another civilization has not only survived but thrived to the point of harnessing the energy of a star. It would confirm that we are not alone, that life has flourished elsewhere in the universe. But even if the search comes up empty, the attempt itself is a testament to our curiosity and determination, to our need to understand the universe and our place within it. Searching for Dyson spheres through infrared light is not just about finding evidence of aliens. It's about following the heat of possibility, the warmth of hope that somewhere out there, life has found a way to endure and expand far beyond the limits of a single planet. Megastructures in space represent the grandest expression of engineering ambition, a vision of technology so advanced that it reshapes not just a planet or a region, but entire star systems. These colossal constructs, whether imagined as Dyson spheres, space elevators, or massive rotating habitats, are more than just physical projects. They are symbols of what a civilization might become when it masters both the resources and the energy of its environment on an unimaginable scale. While our current technology is far from capable of building these structures, they offer a glimpse into the future, a time when humanity, or another intelligent species, might transcend the limitations of planets and find new ways to exist in space. Building something like a rotating space habitat, for instance, would address one of the most fundamental challenges we face in space: the lack of gravity. By spinning, these massive structures would simulate gravity through centrifugal force, creating environments where people could live, work, and raise families in space as naturally as they do on Earth. These habitats could range from O'Neill cylinders, which are long, tube-like structures, to massive toroidal shapes like the Stanford torus. Inside, the environment could be designed to mimic Earth's natural beauty, with forests, rivers, and even weather patterns, making space not just a place to visit but a home. The idea of a habitat in space is, at its core, deeply human. It's about creating a livable world, no matter where that might be. These megastructures wouldn't just be technical marvels. They'd be new cradles for life, a way for humanity to carry its culture, history, and spear it into the stars. Space elevators are another compelling concept designed to overcome the tremendous cost of launching objects into space. The idea is simple. Build a tether that stretches from the surface of a planet up into space, anchored by a counterweight in orbit. While it sounds fantastical, in theory, such an elevator would allow cargo and people to be transported into space without the need for rockets, using far less energy. The problem, of course, is the materials. No known substance is strong enough to handle the forces involved. The tension on the cable would be enormous, and any slight imperfection could cause catastrophic failure. But, like with other megastructures, the idea isn't just about the technology, it's about what it represents. A space elevator would transform access to space, making it as routine as getting on a plane today. It reflects the human desire to bridge gaps, to connect Earth with the vastness beyond, and to make space a part of our everyday lives. Then there are the truly massive, almost unimaginable ideas like Dyson swarms or rings, structures designed to capture the energy of entire stars. Unlike Dyson spheres, which would completely encase a star, Dyson swarms are composed of countless solar collectors orbiting a star, gradually harvesting its energy. These structures push the boundaries of what we can conceive of as engineering. They are less about building something for human habitation and more about creating an energy infrastructure that could power a civilization far more advanced than ours. A Dyson swarm would be the ultimate statement of technological mastery, a civilization no longer dependent on the limited energy resources of a single planet, but instead drawing from the virtually limitless energy of a star. It represents a future where the need for energy no longer restricts progress, allowing for projects and advancements we can scarcely imagine now. What's so compelling about megastructures is that they're not just about the physical challenges of building something so vast. They're about how technology shapes our dreams and how far we're willing to go to realize them. These structures ask fundamental questions about the nature of civilization. How do we deal with resource scarcity? How do we expand and thrive in environments that are hostile or barren? At what point does our technology stop being a tool and start becoming the very thing that defines how we live, work, and even think? They represent a break from the traditional way of living on a planet, forcing us to think of ourselves as cosmic beings capable of reshaping entire environments to suit our needs. There's also a deeper psychological and philosophical aspect to megastructures. Imagine living in a rotating habitat, or beneath the vast expanse of solar panels that make up a Dyson swarm. The experience of space, of living in a structure built to manage the forces of the cosmos, would alter the human perspective in profound ways. It would require a shift in how we think about home, community, and even identity. On Earth, we're deeply tied to the rhythms of nature, the rising and setting of the sun, the cycles of seasons. In space, these natural cues disappear, replaced by an artificial environment that we've designed to keep us alive. In that sense, megastructures in space would be the ultimate expression of human ingenuity, but they'd also represent a break from the natural world as we know it, creating a new kind of relationship between humans and their environment. Ultimately, megastructures are more than just science fiction dreams. They're a reflection of our deepest desires and fears about the future. They force us to confront our limitations while also inspiring us to think bigger, to push beyond the boundaries of what we believe is possible. Whether they ever become reality or remain as thought experiments, they challenge us to imagine what kind of future we want to build and what price we're willing to pay to reach the stars. For humanity, thinking about megastructures is more than an intellectual exercise. It's a way of exploring the outer limits of our potential, of wondering what we might become if we ever learn to harness the full power of the cosmos. Dyson swarms, as a concept, offer a more plausible and flexible approach to the grand idea of harnessing a star's energy than the original vision of a solid Dyson sphere. Instead of one gigantic shell encasing a star, a Dyson swarm would consist of thousands, or even millions, of smaller, independently orbiting satellites, all working together to capture solar energy. It's a more feasible engineering project, allowing a civilization to build piece by piece, rather than attempting the nearly impossible task of constructing a single, planet-sized structure. Each of these satellites could act like a solar panel, absorbing energy from the star and transmitting it back to wherever it's needed: planets, space stations, or further outposts in the solar system. This modular approach doesn't just make the idea more realistic. It reflects the way humans tend to tackle big challenges in stages, with incremental steps rather than one monumental leap. The appeal of Dyson swarms lies not only in their practicality but also in their adaptability. A civilization could start small, with just a few satellites, and gradually build up the swarm over centuries or millennia as their energy needs grow. This slow expansion feels familiar. It's the same way we've built cities, infrastructure, and technology here on Earth, one piece at a time. As the swarm grows, it wouldn't just capture more energy, but it could also serve other functions, like providing habitats, research stations, or manufacturing centers. This flexibility mirrors human ingenuity, where technology often serves multiple purposes beyond its original intent. Alternative concepts to Dyson swarms emerge from the same basic idea, capturing as much energy from a star as possible, but with different technological spins. Dyson bubbles, for instance, imagine a slightly different arrangement, where lightweight, solar-collecting devices hover around a star using radiation pressure to stay in place, like massive space kites. This vision feels even more delicate and less intrusive than a swarm, as if a civilization is carefully managing its energy consumption without the heavy-handedness of building vast metal structures. It's a concept that suggests a kind of balance, a way of harvesting energy without completely dominating or transforming the star system. Then there are the more radical ideas, like the concept of a Dyson net or web. This vision imagines an even finer mesh of technology, almost like a cosmic spider web, spread across vast distances around a star. This approach could involve nanotechnology, where tiny machines operate on a microscale but in such enormous quantities that they collectively gather immense amounts of energy. A Dyson net would represent a shift toward precision and efficiency, implying a civilization that has moved beyond brute force solutions into a realm where technology is almost invisible, seamlessly integrated with the environment. These alternative concepts reflect different ways of thinking about technology and civilization. Some are about gradual, cooperative growth, where each satellite or piece of technology adds to the whole without overwhelming the system. Others are about refinement, where advanced civilizations might have found ways to gather energy without the heavy footprint of enormous, obvious structures. In each case, these ideas push us to rethink what an advanced civilization might look like, not just in terms of their technology, but in terms of how they interact with their environment. Are they conquerors of their stars, wrapping them in massive swarms and harnessing every last drop of energy? Or are they more subtle, finding ways to coexist with their stars in ways that leave less of a mark? Thinking about Dyson swarms and alternative concepts isn't just about imagining far-off alien civilizations. It's also about reflecting on how we as humans approach energy and progress. As we face growing challenges here on Earth, from climate change to energy shortages, these ideas feel like metaphors for the choices we'll have to make. Do we try to extract every resource, building ever larger systems to meet our needs? Or do we find ways to live more efficiently with a lighter touch? Dyson swarms and their alternatives suggest different visions of the future, not just for alien species, but for ourselves. They challenge us to think about what kind of civilization we want to become, how we want to grow, and whether we can balance our technological ambitions with the environment that sustains us. The fact that these concepts are even part of scientific and philosophical discussions today says something important about our own species. We're still at the very beginning of our journey toward mastering energy on a grand scale, but already we're thinking about what it might look like to one day harness the power of a star. Dyson swarms, bubbles, nets. They're all symbols of that far-reaching curiosity of a future where humanity, or some other species, might solve the energy puzzle in ways we can only dream of. And as we search the stars for signs that someone else might have already done it, we're reminded of how much potential still lies ahead of us, both in terms of what we can achieve and how we might choose to shape our future. The materials needed to build a Dyson sphere push the boundaries of what we currently understand about engineering, technology, and resource availability. The sheer scale of such a project is staggering, requiring resources that dwarf anything we've ever used in human history. Imagining the construction of a structure that could encircle a star forces us to think in ways that go far beyond our current limitations. It's not just a question of how you gather the necessary materials, but where they would come from, how they would be transported, and how you would process them in the vacuum of space. The most obvious requirement is an enormous quantity of raw materials, especially metals and other elements that could withstand the intense radiation and heat from a star. Traditional materials like steel or concrete wouldn't work. The stresses and conditions near a star are unimaginable, and the materials would need to be incredibly light yet durable. Hypothetically, something like carbon nanotubes or graphene could be useful due to their strength and resilience. These materials are still in their infancy for us, used sparingly in high-tech applications, but in theory, they could be scaled up massively if a civilization had advanced far enough. It's like thinking of the most cutting-edge materials we have today and then imagining them perfected, their properties pushed to their absolute limits. For us, these materials are experimental, but for a civilization capable of building a Dyson sphere, they would be as common as steel beams are for us. But the question of where these materials would come from presents an even bigger challenge. Earth, or any single planet, doesn't have enough resources to even begin constructing something like a Dyson sphere. You'd have to mine asteroids, moons, and potentially entire planets, stripping them of their raw materials and transporting them to the construction site. This means that a civilization planning to build a Dyson sphere would first need to master space travel and resource extraction on an interplanetary scale. It would be an act of transformation, where entire celestial bodies are reduced to raw material for the construction of a structure so large that it defies conventional imagination. This reflects a kind of technological dominance over their environment that we can barely conceive of today. Energy would be another critical issue. Not just the energy the Dyson sphere would eventually harness from the star, but the energy required to build it in the first place. The production of materials, their transportation across vast distances, and the assembly of the structure itself would demand an immense amount of power. This isn't something that could be done with fossil fuels or even nuclear energy. It would require a civilization that had already moved beyond these technologies, tapping into sources of energy that are clean, efficient, and essentially unlimited. Solar power, fusion, or even antimatter could be the key, allowing for construction to proceed without the kinds of resource limitations that we currently face. A Dyson sphere would also need to be resilient against the immense gravitational forces of the star it surrounds. The materials would have to resist warping, melting, or collapsing under the gravitational pull, which means the design would need to balance incredible strength with flexibility. It's not enough to just have strong materials. You need materials that can work together in a system, absorbing the forces they're subjected to without failing. In that sense, the construction of a Dyson sphere isn't just about raw materials. It's about precision engineering on an astronomical scale, where every piece is part of a larger, finely tuned mechanism. The materials would need to be able to conduct heat efficiently as well, or else the structure would overheat and fail, which adds yet another layer of complexity to the requirements. This kind of endeavor would demand the invention of new technologies, not just in material science, but in manufacturing and assembly. We think of construction in terms of cranes, welders, and factories, physical tools that build physical objects. But for something like a Dyson sphere, those tools would be useless. The construction would likely be done by swarms of autonomous robots or nanomachines, tirelessly piecing together the structure in the vacuum of space. These machines would need to be self-replicating, able to repair themselves, and adaptable enough to handle the unpredictable nature of space construction. The materials for building these robots would also have to be lightweight, durable, and efficient, another challenge that goes hand in hand with the materials for the Dyson sphere itself. But there's a human element to all of this, too. Building a Dyson sphere isn't just about materials and technology. It's about the ambition of a civilization. It reflects the desire to overcome limitations, to push the boundaries of what's possible. The materials needed to build such a structure are not just physical objects, but also a symbol of how far a species has come. It suggests that they've solved their energy problems, mastered space travel, and learned to manipulate their environment on a cosmic scale. The materials become a testament to their creativity, resilience, and determination to survive. At its core, the question of materials for a Dyson sphere is a reflection of what it means to be a technological civilization. It's about understanding the universe and using that knowledge to create something enduring, something that could sustain a civilization for millions of years. For humans, thinking about these materials forces us to confront our own limitations and imagine what might be possible in the distant future. It's not just about dreaming of alien civilizations. It's about imagining what we ourselves could become, and how we might one day find the materials and the will to build something as monumental as a Dyson sphere. When thinking about the theoretical limits of human engineering in space, it's impossible not to be struck by the vastness of what lies ahead. The scale of space is overwhelming, and the challenges we face in trying to push our technology beyond Earth's atmosphere are daunting, but at the same time, it's part of human nature to dream of what might be possible. Our first steps into space, launching satellites, landing on the moon, sending probes to distant planets, feel like early sketches in the larger blueprint of what we might one day achieve. But there are very real limitations that define our progress, and understanding them gives us a sense of both our current place and our future potential. One of the most obvious barriers is energy. Moving anything through space requires an incredible amount of energy, and even the best rockets we have today are constrained by the limits of chemical propulsion. This means that as we imagine more ambitious projects, whether it's sending humans to Mars, building colonies on distant moons, or constructing megastructures, we have to contend with the simple fact that getting there requires a revolution in how we think about energy. Nuclear propulsion, solar sails, and even concepts like fusion or antimatter drives might one day allow us to break free from the limits of chemical rockets, but for now, the energy cost of space travel is a massive bottleneck. Even if we solve the problem of propulsion, space itself presents an environment that is fundamentally hostile to human life. The vacuum, the radiation, the extreme temperatures. These are all engineering challenges that we have to solve every time we send humans or machines into orbit. The materials we currently use, such as metals and composites, are strong enough to build spacecraft, but they're not perfect. They degrade over time due to radiation, and they can't protect us fully from the dangers of space. Future engineering solutions may involve new materials, like radiation-resistant alloys or even self-healing materials that can repair damage in real time. These would allow for longer missions and more durable structures, but we're still in the early stages of developing these technologies. Then there's the challenge of building large-scale structures in space. On Earth, we rely on gravity to keep things anchored, and we have an entire infrastructure for construction: cranes, scaffolding, factories. In space, none of that exists. The microgravity environment changes everything, making it both easier and harder to build. On the one hand, objects are weightless, so they can be moved with very little energy. On the other hand, this same lack of gravity makes it difficult to keep things stable, to put them together with precision. It's not just a question of bringing enough material into orbit. It's about developing new methods of assembly. Robots, 3D printing, and modular construction techniques could play a crucial role, allowing us to build space stations, satellites, and eventually habitats in cities in orbit. But these techniques are still in their infancy. One of the more profound limits is human biology itself. We've evolved over millions of years to live in Earth's gravity, under its protective atmosphere. Prolonged exposure to microgravity weakens muscles and bones, alters blood flow, and causes a range of health issues. And that's just for people living in space for a few months. If we're ever going to establish permanent settlements on other planets or moons, we'll have to either figure out how to mitigate these effects or find ways to adapt. Artificial gravity, created by spinning spacecraft or space stations, might be a solution, but it brings its own engineering challenges. If human beings are going to live and work in space for extended periods of time, our bodies will have to endure conditions we're simply not designed for, and that's a limit we can't ignore. Space also challenges the way we think about time. Even if we manage to overcome the energy and health challenges, the distances involved in space travel are immense. The closest star system, Alpha Centauri, is more than 4 light-years away. That means that with current technology, it would take tens of thousands of years to get there. So, while we might imagine engineering feats that could one day take us to other stars, we also have to face the reality that time itself is a limitation. Even with the best propulsion systems, traveling across the galaxy would take longer than a human lifetime, which forces us to think differently about what exploration means. Would we send generation ships, where multiple generations of humans live and die on a spacecraft before it reaches its destination? Or could we develop technology that allows us to bend space and time, like the hypothetical warp drives or wormholes? These ideas feel like science fiction, but they represent the farthest edges of what might be possible. The more we think about the limits of human engineering in space, the more we're reminded of the fact that, as a species, we're still very young. The universe is ancient, and our knowledge of it is still in its infancy. But the very act of imagining these limits, whether it's energy, materials, biology, or time, drives us forward. We push against these barriers because we have an innate desire to explore, to understand, and to expand our presence in the cosmos. Each challenge is an opportunity, not just to overcome a technical problem, but to redefine what it means to be human. Because at the heart of all these engineering problems lies a deeper question. What kind of species do we want to be? Do we want to stay confined to one planet, one star system, or do we want to spread out, to evolve in ways that we can barely comprehend now? The limits of human engineering are real, but so is the human drive to transcend them. The idea of space colonization has long captured the human imagination, but as technology inches closer to making this dream a reality, it becomes clear that the future of such endeavors is deeply tied to solving our energy challenges. Sending humans to other planets, or even building habitats in space, demands a rethinking of how we produce, store, and use energy. On Earth, we are still grappling with the limitations of our energy systems, and as we look to space, these limitations take on a whole new level of complexity. Without abundant and reliable energy, the possibility of surviving, let alone thriving, in space remains a distant vision. Mars is often seen as the first real step in colonizing another planet, and the harsh realities of its environment make energy solutions one of the most pressing issues. There's no oil or coal to be mined on Mars, no natural gas deposits waiting to be tapped. The thin atmosphere and the distance from the sun mean that solar energy, while a viable option, is not as straightforward as it is on Earth. The Martian dust storms that can last for months would cover solar panels, cutting off access to that power source during critical times. This has led to considerations of nuclear power as a solution, small modular reactors that could provide a steady and reliable stream of energy for a Martian colony. These reactors would need to be safe, durable, and capable of operating for years without maintenance from Earth, a feat of engineering that pushes our current technology to its limits. And yet, the potential is there. Nuclear energy could offer the kind of consistent power needed to sustain life support systems, communication with Earth, and the infrastructure of an entire colony. But Mars is just one part of the puzzle. If humanity is to spread further into the solar system, energy solutions become even more crucial. The further from the sun we go, the less viable solar power becomes. This has led some to propose tapping into helium-3, an isotope found in abundance on the moon. Unlike the reactors we use today, which rely on uranium, helium-3 could potentially be used in fusion reactors, offering a clean and nearly limitless source of energy. The moon, long overlooked, could become a key resource in fueling not just space exploration but energy needs back on Earth as well. Mining helium-3 from the moon's surface and transporting it back to Earth for fusion power could solve two problems at once, opening up space exploration while providing a new solution to the growing energy crisis at home. However, the technology to harness fusion power remains elusive. For now, it remains a tantalizing possibility, one that would require international collaboration, massive investments, and a leap forward in our understanding of nuclear fusion. The colonization of space also brings to light another challenge: how to store and distribute energy in an environment where traditional power grids don't exist. On Earth, we have built an intricate system of energy distribution, but in space, power will need to be managed in entirely new ways. Some have suggested building space-based solar power stations, enormous satellites that could collect solar energy and beam it back to Earth, or to colonies on the Moon and Mars. These stations could orbit closer to the Sun, capturing vast amounts of energy, far more than we could ever gather on the surface of a planet. The energy could then be transmitted through microwaves or lasers to wherever it is needed. This technology, while still in its infancy, offers a glimpse into a future where space itself becomes a source of energy, not just a destination. As we consider these possibilities, it's clear that space colonization and energy solutions are deeply interconnected. The energy needed to sustain human life in space could also provide new solutions for Earth's energy crisis. The innovations required for long-term survival on other planets, whether it's in fusion technology, advanced nuclear reactors, or space-based solar power, could fundamentally reshape how we think about energy on Earth. The challenges we face in space are forcing us to develop technologies that could change life at home, offering cleaner, more efficient, and more sustainable ways to power our civilizations. However, beyond the technology lies the human element. Colonizing space is not just about machines and reactors, it's about people. The people who will live and work in these environments will need to rely on energy in ways we've never had to consider on Earth. In the vacuum of space, energy means life. Without it, nothing functions. There's no oxygen, no heat, no protection from the cosmic radiation that could turn a thriving colony into a barren wasteland. Energy isn't just a resource in space, it's survival itself. The thought of living in a place where every breath is reliant on energy systems working perfectly brings a new awareness to the fragile balance of life in space. Ultimately, space colonization forces us to confront some of the deepest questions about our future. Will we continue to rely on finite resources, or will we find a way to unlock the near-infinite energy sources that space might offer? And as we look beyond our planet, what responsibilities do we have to ensure that the energy systems we develop are sustainable, both for the colonies we may one day build and for the planet we currently call home? These questions are not just theoretical. They are the foundation of whether humanity can truly thrive beyond Earth. The journey to space is also a journey into a new era of energy, one that could define the future of human civilization in ways we are only beginning to imagine. The concept of capturing energy from stars has always felt like the kind of idea that belongs in the realm of science fiction. But as our understanding of the universe deepens, it's becoming clear that this idea isn't just an imaginative leap. It could one day be a reality. Stars are the engines of the cosmos, producing incomprehensible amounts of energy every second. And the thought of harnessing even a fraction of that power is staggering. It's no longer just a fanciful dream. It's something that could reshape the way we think about energy on a cosmic scale. The sun, for example, bathes Earth in more energy every hour than humanity uses in an entire year. The challenge isn't whether the energy is there. It's how we might one day capture and utilize it. Solar panels, the most familiar method of capturing stellar energy, represent just a sliver of what could be possible. These systems have grown increasingly efficient, and we're now able to convert sunlight into electricity with ever greater precision. But on Earth, we are limited by the day-night cycle, weather conditions, and seasonal changes. To truly harness stellar energy, we would need to go beyond these earthly constraints, capturing it directly from space. This is where space-based solar power comes into play, placing large solar collectors in orbit where they would be free from the interruptions that plague Earth-based systems. These collectors could absorb sunlight continuously, 24 hours a day, and beam the energy back to Earth through microwaves or lasers. The technical hurdles are significant, from building the massive solar arrays to ensuring the safe transmission of energy back to the planet. But the potential is undeniable. Capturing energy from space could provide a clean, nearly limitless source of power, dramatically reducing humanity's reliance on fossil fuels and even opening the door to new possibilities for space exploration. Then there's the idea of Dyson spheres or swarms, which pushes this concept to its most extreme form. A Dyson sphere, in its most speculative vision, would be a massive structure completely surrounding a star, capturing nearly all of its energy output. In reality, a full sphere is likely impossible, but a Dyson swarm, composed of thousands or even millions of smaller solar collectors orbiting a star, could achieve a similar effect. This isn't just about providing energy for a single planet. It's about harnessing the full power of a star, tapping into the same energy that fuels solar systems. The scale of such a project is hard to fathom. It would require materials and resources beyond what we currently possess, possibly mined from asteroids or moons. Coordinating the construction of such an array, managing the flow of energy, and ensuring the long-term stability of the system would challenge everything we know about engineering and collaboration. But the rewards would be transformative. A civilization that could build a Dyson swarm would have access to energy on a scale we can barely imagine, enough to power space habitats, interplanetary travel, and perhaps even projects we haven't yet conceived. Nuclear fusion is another path towards stellar energy capture, but rather than harnessing energy directly from stars, it seeks to replicate the process here on Earth. Fusion is the reaction that powers stars, including our own sun. If we can master it, we could have a nearly limitless source of energy, without the harmful byproducts that come with nuclear fission or fossil fuels. Fusion reactors would essentially be miniature stars, creating the same kind of reactions that occur in the hearts of the cosmos, but in a controlled environment. Scientists have been working on this for decades, and while we're still some distance from making it practical, recent advances suggest that we might be closer than we think. A working fusion reactor would be a game changer, producing enormous amounts of energy with little waste, solving many of the world's energy problems. It's a daunting challenge. Containing such high-energy reactions and sustaining them for long periods requires technology that is still being developed. But the promise of fusion, a process that taps into the same forces that power the universe, is too compelling to ignore. There's also the potential for harvesting energy from more exotic stellar sources, like neutron stars or even black holes. Neutron stars, with their extreme magnetic fields and rapid rotation, could theoretically be tapped for energy. These stars are remnants of supernovae, incredibly dense and powerful. And while the idea of capturing energy from one feels like something out of the far future, it's not outside the realm of possibility. Some scientists have even speculated about the use of black holes as energy sources. By spinning up matter around the event horizon of a black hole, it might be possible to extract energy through a process known as the Penrose mechanism, converting some of the black hole's rotational energy into usable power. The thought of using one of the most mysterious and destructive forces in the universe to generate energy is mind-bending, but it reflects the depth of human curiosity and our willingness to explore even the most outlandish ideas in pursuit of progress. As we look to the future, it's clear that stellar energy capture is about more than just science. It's about survival. Earth's resources are finite, and as our population grows, the demand for energy will only increase. If we are to continue advancing as a civilization, we will need to find new ways to meet that demand without destroying our planet in the process. Stellar energy capture offers a glimpse of what might be possible if we look beyond the limitations of Earth, tapping into the vast energy reserves of the stars. It's an endeavor that will test our ingenuity, our capacity for collaboration, and our willingness to embrace the unknown. But if we succeed, we could unlock a future where energy is no longer a limiting factor, where the power of the stars themselves fuels our journey through the cosmos. The idea of humanity achieving stellar energy dominance presents a future so transformative that it almost feels like the dawn of a new age. To control and harness energy directly from the stars would be a leap beyond anything we've ever known, pushing our species into a realm of abundance that could reshape the foundations of human life. At its core, this isn't just about energy. It's about power, progress, and survival. Dominating stellar energy would mean moving beyond the constraints that have limited civilizations for millennia, where energy scarcity has always defined the limits of growth. With access to the near-limitless output of stars, the scarcity that has driven so much conflict, inequality, and competition on Earth could begin to fade. The implications are far-reaching, touching not just on technology and industry, but on how we live, how we interact, and how we envision our future. For one, a world, or even a galaxy, powered by stellar energy would radically shift the geopolitical landscape. Energy has always been a source of control and leverage, from the dominance of oil-rich nations to the reliance on coal and natural gas in industrialized societies. But if stellar energy became the primary source, these dynamics would collapse. Energy wouldn't be tied to specific locations or controlled by a handful of powerful states or corporations. With the vast energy of stars at humanity's disposal, energy could flow freely, shared across planets or space colonies in ways that would make Earth's current energy grid look archaic. The conflicts over resources, the endless struggle to control oil fields or dominate natural gas pipelines, could dissolve into history, replaced by a new era where energy scarcity is no longer a driver of global instability. Of course, this would not happen overnight, and the transition would likely be turbulent. The existing power structures that profit from traditional energy would resist such a shift. But once achieved, the implications would be nothing short of revolutionary. Stellar energy dominance would also open the door to possibilities that seem almost mythical today. We could power massive space habitats, sprawling cities in orbit around distant stars, and interplanetary travel on a scale previously unimaginable. Energy wouldn't just be a necessity, it would be an enabler of dreams. Imagine a future where humanity is no longer bound to Earth, where entire civilizations live on space stations or artificial worlds powered by the light of distant suns. The energy from these stars would allow for not just survival but flourishing, terraformed planets, habitats with artificial climates tailored to perfection, and agriculture that produces food on an enormous scale. Energy would be the key to unlocking the next chapter in human evolution, where space isn't just a place we visit, but where we live, explore, and thrive. But with such power comes new ethical questions. The ability to dominate stellar energy doesn't just transform human capabilities, it also challenges us to consider how we use this power responsibly. There would be the temptation to exploit it recklessly, much like we have done with Earth's resources. The danger lies not in the technology itself, but in how humanity chooses to wield it. Will we use it to expand and explore, or will we fall into the same patterns of greed and destruction? Stellar energy dominance might offer the potential for utopia, but it could just as easily lead to catastrophe if misused. The massive scale of energy at our disposal would amplify both our best and worst instincts. There's also the question of who controls such energy. If one nation or group managed to monopolize access to stellar energy, it could wield a level of power that dwarfs anything in history, creating imbalances that would make today's inequalities seem trivial. Even on a personal level, stellar energy dominance could reshape how we live our everyday lives. The conveniences we enjoy now, powered by electricity and fossil fuels, would pale in comparison to what could be possible with a direct tap into the energy of stars. Our homes could be self-sustaining, our transportation powered without pollution or concern for fuel. Imagine never worrying about charging devices or rationing energy during a crisis. Entire cities could run on clean, abundant power, unshackled from the environmental toll of carbon emissions. The climate crisis, which looms over our current era, would be addressed not through sacrifice but through innovation, by replacing the destructive energy systems of today with something far cleaner and more sustainable. It's a future where humanity could live in harmony with the environment, powered by the very stars that have sustained life for billions of years. Yet, the most profound implication of stellar energy dominance may be what it does to our sense of time and space. Once we can capture and utilize such immense energy, the boundaries of our technological achievements could extend to things we once thought impossible. Interstellar travel, for instance, could become feasible, with energy enough to propel us to other star systems, bringing us closer to the dream of exploring the galaxy. This would not only redefine our relationship with space, but also with each other. Humanity could spread across the stars, connected not just by a shared origin but by shared energy, creating new societies that carry forward our legacy in ways we can barely conceive. Energy, once a limiting factor, could become the force that unites distant worlds, a common thread that binds the future of our species. In the end, stellar energy dominance is more than a technological achievement. It's a step toward a new identity for humanity. It represents the point where we transcend the limitations of a single planet, a single sun, and begin to think of ourselves as part of something much larger. The stars that have always been out of reach might finally become part of our reality, not just objects of wonder, but the engines of our future. And as we reach for that future, the greatest challenge won't be whether we can capture the energy of the stars. It will be whether we can rise to the responsibility that comes with such power, using it to build a future that benefits not just a few, but all of humanity. As humanity looks toward space with an increasing sense of urgency, the question of how to meet our energy needs beyond Earth is becoming critical. The vastness of space is filled with promise, but it is also a place of extreme isolation, where survival depends entirely on the resources you bring or can harness. On Earth, we take for granted that energy is available at the flick of a switch, but in space, energy is life itself. Without it, there are no systems to regulate temperature, generate breathable air, or maintain communication back to Earth. As we push farther from our home planet, our energy needs will only grow more complex, forcing us to invent solutions that go beyond anything we've developed so far. One of the first real challenges is how to provide consistent, reliable energy on other worlds. On Mars, for instance, solar energy seems like an obvious choice, but it comes with serious limitations. The planet's distance from the sun means solar panels would be less efficient than on Earth, and the planet's massive dust storms can block sunlight for weeks or even months at a time. This would leave any human outpost vulnerable to power shortages during crucial periods, making it clear that relying solely on solar power is not a viable long-term solution. Engineers have started to look at alternatives, such as nuclear reactors, which could provide a steady and dependable source of energy. These reactors would need to be small, lightweight, and capable of running for extended periods without human intervention, a significant engineering challenge, but one that is already being explored with prototypes designed specifically for space missions. Nuclear power could offer the stability and longevity that solar lacks, powering habitats, water processing, and even the oxygen generators necessary for life on Mars. But Mars is just the beginning. As we set our sights on more distant targets, like the moons of Jupiter or Saturn, the energy demands grow exponentially. Solar energy, which works relatively well in the inner solar system, becomes almost useless in the outer regions, where sunlight is weak and distant. This leads to the need for even more advanced solutions, such as fusion energy, tapping into the same process that powers stars themselves. If humanity can master fusion, we could bring the energy of the stars with us wherever we go, providing an almost limitless source of power to sustain life, technology, and exploration in the darkest reaches of space. The technology to harness fusion energy is still in development, and it may take decades or even centuries to fully realize its potential, but the promise is tantalizing. A spacecraft or colony running on fusion power wouldn't just survive, it could thrive, with enough energy to terraform environments, fuel vast exploration fleets, and support large populations in space. Energy storage is another significant issue we'll face in space. Even if we can generate vast amounts of energy, we'll need ways to store and transport it efficiently. Current battery technology, which powers everything from smartphones to electric cars, is nowhere near capable of handling the energy needs of space colonies. Developing new materials and systems for energy storage will be crucial, allowing us to store surplus energy during times of abundance and draw from it during times of scarcity. Advances in supercapacitors, energy-dense materials, and wireless energy transmission could play a role in this future. In space, where there are no power grids, energy must be delivered precisely where and when it's needed, and this will require a level of innovation that pushes our current understanding of technology. Another intriguing possibility lies in harvesting energy from space itself. We've long imagined building solar power stations in space, massive arrays of solar panels that could orbit close to the sun, capturing vast amounts of energy and beaming it back to Earth or to distant colonies. This energy could be transmitted via microwaves or lasers, delivering power across space without the need for physical infrastructure like wires or pipelines. Such a system could provide energy not just for human settlements, but also for spacecraft on long-duration missions, refueling them mid-journey and extending their range far beyond what's possible today. The technical challenges are immense, from building these massive stations to ensuring the safe transmission of energy across vast distances. But if successful, space-based solar power could revolutionize how humanity powers its expansion into the cosmos. Ultimately, the future of humanity's energy needs in space is about more than just survival. It's about unlocking the full potential of what we can achieve as a species. Energy isn't just fuel. It's the foundation of everything we build, create, and explore. If we can solve the energy puzzle, the limitations that have always bound us to Earth will begin to fall away. With abundant energy, we could build cities on the Moon, Mars, and beyond. We could explore the farthest reaches of the solar system, sending crewed missions to places we've only dreamed of visiting. And one day, we could even look beyond our solar system, traveling to other stars, powered by the energy we've learned to harness and control. But this future isn't guaranteed. It will require unprecedented levels of cooperation, innovation, and vision. The energy systems we develop for space will have to be adaptable, robust, and incredibly efficient, capable of functioning in environments that are hostile and unpredictable. And they will need to be sustainable, not just in terms of materials and cost, but in how they interact with the ecosystems, both natural and artificial, that we create. If we get it right, the energy solutions we develop for space could also revolutionize life on Earth, providing new ways to meet the growing energy demands of our planet while reducing our impact on the environment. Humanity's energy needs in space will challenge us to think beyond the present, to envision a future where energy isn't a limitation but a gateway to new possibilities. The journey to space is, in many ways, a journey into a new era of energy, one that could define not just our exploration of the cosmos, but the next chapter of human civilization itself. The stars are out there, waiting for us, and the energy they offer could be the key to unlocking a future beyond anything we've ever imagined. But it will take more than technology to get us there. It will take a new way of thinking about energy, one that's as vast and ambitious as the cosmos itself. In science fiction, the concept of Dyson spheres often embodies the sheer audacity of human or alien ambition, a vision so grand it forces us to reconsider the limits of civilization. The Dyson sphere, an idea proposed by physicist Freeman Dyson, imagines a structure or swarm of structures encircling a star, capturing all of its energy output to fuel the needs of an advanced civilization. For many writers, this vision of harvesting the total energy of a star serves as a symbol of ultimate technological mastery, an emblem of a society so advanced that its needs have outgrown anything a planet could offer. It's not just an energy solution. It's the ultimate expression of growth and conquest in the cosmos. In some portrayals, the Dyson sphere is a relic of a civilization long past, the last remaining monument to a species that reached unimaginable heights before disappearing into the abyss. Stories like these carry a sense of melancholy, where the sphere stands as a testament to greatness, but also to hubris. The energy needs that once justified such a massive undertaking have faded, and now the sphere looms empty and silent, a hollow shell drifting around a dying star. There's a kind of eerie beauty to these portrayals, as they force us to wonder. If we ever built such a structure, would it mark our pinnacle, or would it be a sign of our eventual fall? The idea that a Dyson sphere could be both the source of salvation and a symbol of forgotten glory speaks to the fragility of even the most advanced civilizations. Other portrayals are more optimistic, imagining Dyson spheres as bustling with life, filled with unimaginable technological wonders and thriving communities. In these worlds, the sphere is not just a tool but a home, capable of supporting entire ecosystems and billions, even trillions, of inhabitants. The sheer size of such a construct offers endless possibilities for exploration, with people living on the inner surface, basking in the perpetual sunlight of their captured star. For these civilizations, the sphere isn't just about survival. It's about evolution, about taking control of their destiny by harnessing the ultimate energy source. It allows for a kind of prosperity that we can barely comprehend, where the limits of growth, creativity, and power have been shattered by the scale of this artificial world. In some stories, the Dyson Sphere becomes a prison, a place where its inhabitants are so dependent on their captured star that they can never leave. The vastness of space, once filled with opportunity, becomes distant and inaccessible. The energy needs that drove the creation of the sphere have now confined them, locking them into a perpetual cycle of consumption. The star at the center, once a source of life and hope, now looms like a caged beast, its immense power trapped and controlled but never truly free. There's an irony in this portrayal, where the ultimate achievement of a civilization becomes the very thing that traps it, stripping away its ability to move forward. Then there are the darker interpretations, where Dyson spheres are the tools of conquest or control, built not by benevolent civilizations, but by those seeking to dominate entire star systems. In these portrayals, the sphere is less a marvel of engineering and more a weapon, its energy used to fuel war machines, build armies, or destroy worlds. The star, once a symbol of warmth and life, becomes a source of terror, its energy bent to the will of a power-hungry civilization that sees no limits to its ambition. This version of the Dyson Sphere speaks to the fears that underlie much of human advancement. The worry that the pursuit of power can easily become destructive, that the tools we create to save ourselves can just as easily be used to destroy others. And then there's the portrayal of Dyson spheres as almost incomprehensible structures built by alien civilizations so advanced that they defy human understanding. In these stories, the sphere is often glimpsed from afar by civilizations that can't even begin to comprehend its purpose or the beings that constructed it. The sheer scale of the sphere is overwhelming, its surface covered with strange, alien technology, its inner workings unknowable. These portrayals remind us that, even as we dream of building such structures, there could be civilizations out there that have already done so. Civilizations that operate on levels we can't yet fathom. The Dyson Sphere in these stories becomes a kind of cosmic mystery, a signpost pointing to something much larger and more complex than humanity could ever imagine. For some writers, Dyson spheres are symbols of hope, representing the idea that we can rise above the challenges of survival and scarcity by mastering the stars themselves. They offer a vision of a future where energy is no longer a limitation, where humanity, or some other species, has unlocked the ability to thrive on a scale that spans solar systems. In these stories, the Dyson Sphere is a beacon of what's possible, a testament to the ingenuity and ambition of life itself. It's a dream of a future where the vastness of space is no longer an obstacle, but an invitation to grow and explore without fear of running out of the resources that sustain us. But perhaps the most powerful portrayal of a Dyson sphere is when it serves as a mirror to the present, reflecting our own struggles and ambitions back at us. In many ways, the Dyson sphere embodies the ultimate question of how far we are willing to go in our pursuit of energy and progress. It asks whether we'll ever reach a point where we're satisfied with what we have, or if the drive for more energy, more power, more control, will always push us toward greater and greater feats. It forces us to think about the balance between creation and destruction, between progress and restraint. As we dream of harnessing the power of the stars, we must also ask ourselves whether we're ready for the responsibility that comes with it. And that brings us to the end of our journey through the cosmic wonders of Dyson spheres. From harnessing the full power of a star to glimpsing the limits of human imagination, we've explored a future where the boundaries of energy and space are redefined. If you enjoyed traveling to the far reaches of possibility with us, don't forget to give this video a thumbs up and subscribe to Quiet Universe, where we continue to dive into the mysteries that stretch beyond the stars. Thanks for watching, and until next time, keep your eyes on the infinite.